give you the background a little bit, and then we'll talk about how to construct different types of graphs, and then also how to interpret them. Right? This is where we're dealing with the relationship between two variables. Right? The previous graphs were just analyzing a single variable. Right? So you had, I mean, we were looking at everything out of context, but it was just a raw set of data. It wasn't how one set of data related to another set of data. And this has applications in other fields, economics we're just talking about, where if you're talking about supply and demand, you know, one is increasing as the other is decreasing. Right? That's the relationship between two different variables, one independent of the other. Right? So this concept is going to help us kind of evaluate those sorts of things. All right, from a purely mathematical standpoint, but then later on, you'll be able to contextualize and start to think about the true natural meaning behind these things. All right, so correlation, correlation, when one variable is related to another variable in some way. Now, just because variables are related doesn't mean they're strongly related. They could be loosely related. And it also doesn't mean that there's, and you might have heard the phrase correlation does not imply causation. That's just basically saying that just because two variables are related doesn't mean one thing caused the other to happen. Right? Cause and effect is much harder to prove, and you really need a proper statistical analysis, an actual study, in order to prove a causal relationship. Right? But you could show that two things are related to one another. You know, a person's height and their corresponding weight. Right? As a child grows, they get taller, they get heavier. Did the weight gain cause the height to increase? Did the height cause the weight gain? I don't know. I mean, maybe, but there's no, you can't look at the data and say just because they're related that one thing definitely caused the other to happen. And in fact, one person could say that the height caused the weight to increase. The height increase caused the weight to increase. Another person could say, well, if their weight increases, maybe it's because they were intaking more nutrients, which caused their height to increase. So they come up with the exact opposite viewpoint. Right? So we can't make the conclusion of cause and effect just by looking at the way the data is plotted in the graph. More information would be required, but it's a starting point. Right? Scatter plot is just a graph comparing two variables, x against y in most cases. So when you were in an algebra class and you were plotting points, if you plotted 20 or 30 independent points, you were creating a scatter plot. Now, most of the time, you were fitting a curve to that, like a parabola or something along those lines, in which case you were actually using a function model. But that would only be in the perfect correlation sense. You would have a parabola that fit through all of the points perfectly, or a line that fit through all of them perfectly. What happens if it isn't a perfect relationship? Right? You might have something that's strongly related in a linear sense, but not perfect. That's fine. You can draw conclusions from this. A moderate positive correlation. You might have some negative relationships. That was supposed to be a line, but it looks a little wobbly. Strong, moderate, and so on. I mean, there's definitely a downward trend here, but it's very loosely related. Right? That's where you have things like at the pediatrician when they show you the growth chart, that it's not just a line. People don't just fit on a line, your height and your weight. It's like kind of a rainbow looking thing, and you just fit on the rainbow somewhere. If you're not on the rainbow, then you're either above average or below average, but you got to be on the rainbow somewhere, right? That's allowing for strong and moderate relationships to exist. Nobody's perfect, so they don't assume that that's going to be the case, right? You could also have some nonlinear plots, cases that wouldn't fall into a perfect line, for example. Maybe you have a quadratic regression or a quadratic plot or correlation. You might have cubic, quartic. These are all different types of polynomial functions from algebra and pre-calc, if you take those courses. Exponential. This is supposed to be natural logs, but really what I did, and I did this on purpose, shockingly, I just copied and pasted my strong positive linear and made it my natural log, because you can go either way with this. You can say, all right, well, it's a strong positive linear, right? It's centered around a line pretty well. But then you might say, and this is assuming that you have a sense of what a natural log is, it's hit or miss. It looks something like this. All right, it's increasing without bound, although I can't draw, so mine looks like it's leveling off. You can make a case either way. You have a raw set of data. Depending on what the data is modeling, you might say it's linear, you might say it's natural log. In the case of a natural log, you're talking about something that increases dramatically initially, and then its rate of increase slows down. It never stops increasing, but it doesn't increase as fast later on as it did earlier. Right? So you think about things in real life that would play out that way. Yeah. I don't have a better. I mean, I was gonna go with the kid growing up, but like, I can't beat that one. So yeah, the case of none, I think that one is obvious. I don't see a pattern in there in any way, shape, or form. But you could also have. There's another situation that would fall under the category of none. That's not shaping up to be what I want it to be. You might have something that does form a pattern, but that pattern is not a function. And that's because it fails the vertical line test. Fails the vertical line test. You can't draw a vertical. You should be familiar with them to some extent. Yeah. However, since there is a calculator approach that's going to kind of get us through this, you'll see that the names will kind of work themselves out. Like when we go through the calculator approach, you may not even need to know what a cubic model is. You'll just know that the calculator is telling you that the cubic model is your answer. So there's a workaround, but the better way would be to have a sense of what the graph is really telling us. Like, for example, the quartic, anything that looks even remotely like one of these two graphs, M shape, W shape, in any sense, if it has even the slightest resemblance to that, then we would call it quartic. Right? But the calculator is going to give us some metrics that will help us nail down which kind it is. And you look at that data set, which is a copy-paste job of my moderate positive, and you say, well, that doesn't look, no, that doesn't look like that. Yeah, it does. You just got to kind of squint and imagine. You know, basically you can make a case for it. And if you can make a case for it, that's going to be good enough. All right. Look at that formula. That's a beaut. Imagine having to work with that. That's what we call motivation. Wait, there's a calculator approach that's going to do that for us? That's wonderful. Oh, even better, it's built in. It's a default setting. So this is going to give us the correlation coefficient, also known as the Pearson product moment correlation coefficient for people who like to be, I don't know, jerks, people who are full of themselves, I don't know. I just put it there because it's all the name, because if you come across something in a textbook or online resource that says that, at least you'll know what they're talking about. The formula, that formula is actually generated from concepts in Calc 3. So, and you'll see a lot of, it's kind of a recurring theme in this course, where here's a formula, it's an ugly formula. Where did it come from? It would be really nice if we knew like how these tools that we're using, how they started, how they came into being. My answer in a lot of cases is going to be calculus. You have to know calculus in order to understand where it's coming from. So this is something in multivariable calculus. It's fun. But anyway, we don't need to know that because calculus is going to do all the work for us. This is hugely important, the R squared. The calculator gives it to us in percent form. It's a percent of variation in the y variable that can be explained by variation in the x variable. One of the many things that's very frustrating about this calculator is that every stat book, statistician on Earth uses lowercase r squared. But for some reason, the TI-84, 8384, uses a capital R squared, which isn't enough usually to throw too many people off, but it's enough to make you pause for a second. Wait a minute, is this the same R? Like, we learned it as lowercase, now it's capital. What's the story here? It is the same R for some reason. I don't know why they do it that way. Maybe I should know, but I don't care enough to know. All right, so we also have least squares, line of best fit, linear regression equation, all meaning the same thing. This is a method on the calculator that will return to us the line, mathematically, the line that best fits the data set. All right, so instead of eyeballing it like I did on a previous page and just slap a ruler on it, okay, that looks like it's the right kind of line. The calculator will determine for us what the best fit line is based on calculus, right? This chart is just to give you a sense of the relationships that exist with correlation. It's not designed to be an end-all. Basically, the idea here is the closer that your R value is to 1 or -1, the stronger the relationship there is, right? The closer it is to 0, the weaker the relationship. Right? So I said R squared is really important. The reason I say that is because if R squared is equal to 1, you're looking at a perfect correlation. If R squared is close to 1, it's strong. Those are really the two situations that you should be most interested in, because the rest is just some variation of weakness. If I tell you that I conducted a study, I collected data, and I want you to take the results of this data and change the way you operate your business, and I have two variables, and I tell you that they're kind of related to one another, and they have this moderate relationship is what allowed me to draw my conclusions, and my conclusions are what you're going to base your change in policy on. You'd be like, well, it's stupid. You don't even have a strong relationship. It's not, the relationship between the two variables is not strong, so why would I consider what you have to say? So basically, if you're not looking at something that's 0.75 or better, in the case of R, then you're really not looking at anything that's overly meaningful. All right. It's frustrating though when you do a project for a class, or even if you're doing a thesis, master's thesis, doctoral dissertation, stuff like that. You collect all your data, and then you find out that there isn't really much of a correlation between the two variables. You're like, well, I just spent 30 hours collecting all this data. What do I do now? Well, what do? You finish the study, you turn it in, and you hope nobody cares too much, right? But the reality is you should scrap all the data and come up with a different topic, because you drew a conclusion. It's that there's no relationship between the two variables. Like, for me personally, I think there is a strong relationship between crappy drivers and Kia owners. That's a personal belief. I have not collected the data. It's completely anecdotal at this point. I apologize to any Kia drivers out there. It's just every time I get cut off on the highway, yep, there's another Kia. I needed to take a lift to go to the doctor's office the other day. A freaking Kia pulls up. I'm like, you gotta be kidding me. Like, this is how it all ends. I'm gonna die right now because I'm gonna get into a Kia, and this guy, he's gonna cut somebody off, and then we're gonna get into a fatal, terrible, flaming accident, and that's how my life is gonna come to an end. Hyundais are second. Sorry, Hyundais. So, but I did some loose research online, looking. I wanted to I was hoping somebody else did the study, so that I could come in today and be like, yeah, Kia drivers, get rid of it. That's a different kind of joke. That's what every study online said. It's the BMWs. Numero uno in terms of worst drivers.
They're horrible.
Yeah, that's what all the actual empirical studies online said.
They also need the most repairs. Never get a BMW.
Well, you're gonna sit there, speed by, you can control it like it.
I feel like they're racing all the time.
Yeah. I mean, I have a Honda, and I know that when something breaks down in the Honda, yeah, there it is. I go into the shop, and the next day they have the part, and that day they fix it, and I get it back. I had a Hyundai once back when I was younger, and it was like, all right, so we got to order the part. It's going to take 3 weeks. But that was in the 90s, so that's different now. But I do know that, like, anybody I know that has a BMW, and this is, again, anecdotal. I haven't collected the data on it. They all say the same thing. The person who fixed it didn't know how to fix the car. They didn't get the right part. They couldn't get the part at all. Like, it was just a disaster. I don't know. But yeah, signals. I think here's an idea for a study. Measure of intelligence. Whether or not a person speeds through a parking lot. If you speed through a parking lot, you are stupid. Like, I would like to see a study conducted on that. Like, the IQ or some sort of intelligence metric of the individual who speeds through a parking lot, because you must be an imbecile. You speed through a parking lot? I'm sorry, man.
No. And are you counting like time itself?
Like, in terms of like the metric of how fast a person going through a parking lot?
No, time itself. Like,
Oh, time of day. Well, we'll get into all of that stuff when we get to the topic involving collecting data, but you would need to randomize the times in which the data was collected. Randomization is important because you'd have lurking variables like people getting out of church, for example. You want to see the worst drivers in the world, especially in a parking lot, right out of church. Just stand there. Like, well, I did my praying for the week, so I'm good. Now I can do whatever the hell I want, baby. For whatever, I don't know what goes through people's minds. It's like, if you're going to get cut off in a parking lot, it's going to happen outside of the church.
Also the place, Professor, is where the parking lot is. If you go to Palisade Mall on a weekend,
And you're fighting for a parking spot? Yeah. No, I get that, but like, I was pulling out of or walking out of a hockey rink this morning, and there was like nobody in the lot, except for the one guy who goes flying through, who somehow, for whatever reason, needed to get through that area before I crossed. That's the thing. That's where I think the intelligence part comes into play, because I think if I'm on the main road and you want to make a left-hand turn in front of me because you think I'm driving too slow and you don't want to get stuck behind me, I get that. But if you're going to jump in front of me to go 30 miles an hour, then I'm questioning your intelligence. I mean, there's really nothing more to it than that.
All the way down the road across the street.
Yeah, it's like, oh, I can't let you in. Like, what are you, 4? Like, how'd you get a license? I
Or
don't.
it's like you don't want to be one car late.
Yeah. Well, if I don't get in front of this one car, that's going to be all the difference. Sometimes that is true, though. So, anyway, we do all this stuff on the calculator, but again, calculators give us numbers. The numbers don't add the context to the situation. So it's the common sense, the nature of things that allow us to make a determination of what's really going on. Here is the full-blown calculator process. And you look at it, it says 13 steps. I'd rather do it by hand. This little caveat here, steps 2 through 8 and 10, you should only have to do once. All right, so that's good news. So let's set up our calculators to be ready to rock and roll for this. All right, we would have to put our data in L1 and L2. So let's get to an example that involves some data. Yeah, well, I'll just take example 2. I didn't know there was an example 1. All right. So we'll talk about the context in a minute, but we're going to put these data points in L1 and L2. Oh, is this another edit?
Yeah.
Ugh. Cheese and rice. Do you have this example?
Yeah.
Okay. So should be the next page. All right. Well, in any event, we just need the data points anyway. So I'll talk about all this other stuff in a few minutes. So get our data in. One, 2, 3, 5, 9, 11. And 3, 5, 7, 10, 16, 20. All right, so at this point, regardless of what all the words say, we're just learning how to come up with the correlation coefficient and the line of best fit. All right, linear regression, line of best fit, they mean the same thing. All right, so we have our data in. We can follow the process. We're hitting second y equals. Anytime you want to create a stack graph, that's where you're going. So second followed by the y equals. All right, we're only working out a plot 1, so number 3 in this list doesn't apply. We're going to hit option 1. We're going to select scatter plot. All right, our X list should be L1, our Y list should be L2. All right. So really creating the scatter plot is no different in terms of process than all the other graphs that we were working on. Second, y equals, choose the right graph, make sure it's pointing to your data, and you're good to go. At the bottom it says mark. That's just how the points will be plotted on the graph. I go with the boxy looking one because that's a little bit more visible. The little point there, they sometimes look like stray marks when you look at the graph. I don't like it. So one of these first 2 are fine. So then you hit zoom 9, zoom stat, and now you have a scatter plot. All right, so all of that stuff here, everything that we did up here was to create the scatter plot. And so if you don't mess around with the settings that we've been using, then you should be fine, because if I go back to, let's say, a histogram, it's going to default back to list 1 with a frequency of 1. If I select a box plot, it defaults to L1 like I want it to. If I do a normal probability plot, L1 with X. So the settings are the way I want them to be. So I can just go right to the graph and ignore everything else, which is wonderful. So I'm just toggling back and forth at different types depending on what kind of graph I need to come up with. So when I hit scatter plot, I'm good to go. Zoom 9, I have a graph. All right. So that's what I mean by you should only need to do these steps once because you're verifying that they are the way you want them to be. And then from there on out, you're good. Step 10, I'm going to walk you through this now. This is also a one-time deal. I'll walk you through it, and I'll find out in a couple of minutes whether you screwed it up. Because most of us will get what we need. Some of us won't. The ones that won't are the ones who didn't do this right. There's a shorter way of doing it on the TI-84, but I'm going to do it the TI-83 way, and that's what this is. So you're going to hit second 0. Let me get out of here. Second. So follow along with this, yeah. Second 0. And we want to go down to where it says diagnostics on. All right, so scroll down, or you see this X -1 key right above it, it says D. We have an alpha lock on here. If I hit that key, it's going to shoot me right down to the D section. It's a little shorter, but you could just scroll down too. But you're looking for diagnostic on. Just be careful, there's a diagnostic off there too for some reason. So it's diagnostic on. So once you get there, sit tight and I'll get everybody on the same page. All right, so this absolutely needs to happen. Otherwise, you're not necessarily going to get the R and the R squared values that we need to get in order to determine the relationship between two variables. All right, so we're all the way down to diagnostic on, not diagnostics on. So that's a typo. I'll take that if somebody wants to submit. All right, that's a legacy typo. That's been there for the last 16 years, I think. So hit enter. That brings diagnostic on into your home screen. That's the command. I haven't executed the command yet. So hit enter a second time, and it'll say done. So all we did was we enabled the diagnostic features in our calculator. So when I go through the process of coming up with the regression, correlation and regression models, it's going to give me the right display. Honestly, I think this should be the default display, but it's not, and so we have to make this adjustment. All right. So if you've done this, then you should be in good shape. So you can follow along with the rest of the procedure. This is the TI-83 way of doing it. So it's going to look a little different on my display here. Stat, calc. We've done the 1-bar stats already, but there's a whole lot of reg in here. You have lin reg, quad reg, cubic reg, quartered reg. If you think back to those graphical displays we talked about, you know, the scatter plots, this is how we can flesh out numerically which is the most appropriate model. What I want is option 4, lin reg AX plus B. On the TI-83, it looks completely different when you select option 4. On the TI-84, it looks something like this. We need to make a couple of edits, but it's going to be the way we need it. So the TI-83, it'll actually look like what I have written there. It'll say lin reg AX plus B. And then you type in L1, L2, Y1. Right? L1 you get by hitting second 1. L2 you get by hitting second 2. And Y1, that's the fun one, on the 83s only. Bars, scroll over to Y bars, select function, and finally Y1. All right, so that's one of the things that the TI-84 does better than the TI-83. All right. So, TI-84s. Default setting should have X list and Y list as L1 and L2. If that's not the case, that's fine. It's still second 1, second 2, just like on an 83. Frequency list, I don't have any frequencies, so let's clear that out. All right, yours should actually be blank. If it's the first time you've used this feature, somebody else must have been using it. That's why it's different. All right. To store store the regression equation, you want it. It's a little different on the TI-84s. We still need to put the Y1 in there, but it's a different approach. All right. I'm gonna pop it in over here. So second 1 for this guy. If it's not there, second 2, and then we need the Y1 here, which we get by selecting alpha, trace, and then Y1. All right, so again, not user friendly, but that's the way of it. All right, so D should already be there. This we want blank. To get the store regression equation, we do alpha followed by trace. And then you see a list of all your Y's comes up. Shortcut menu, select the Y1. And then you go to calculate. And you'll get this display. So I'll walk through that again in a second. All right, so let me just pop that in over here, though. So you type your data in L1 and L2. Quit out of there. I always quit out, or at least I always intend to. Stat, over to calc, option 4, linreg AX plus B. Default settings are L1 and L2. If they're not there, you hit second 1, second 2. To get store regression equation. And also, this is a good way to figure out if you have a TI-84, if hitting these keys doesn't produce what it's supposed to produce, then you may need an upgrade, an operating system upgrade. So you talk to me at the end of class. So I want to store my regression equation in as Y1. So I hit alpha, followed by trace. And then this menu comes up. I select just the Y1, which is the first entry, so just enter. Once I have that, I go to calculate, and it gives me this display. As an intermediate step, after I hit calculate, it actually put this up on the home screen for like half a second before executing this command to give us that. So the menu is really just a shortcut to give us this, which then gives us that, right? But this gives us everything that we need because it's telling us the equation of a line, the model of the equation of a line. It's telling us what the A and B values are. It's telling us what the R squared and the R values are. If you don't have the R squared and the R's, it's because you didn't turn your diagnostics on, right? So you screwed up that part of the process. That's what I was talking about before when I said, we'll know in a couple of minutes if you didn't do this right, right? That's the issue there, right? So what this is telling me, linear correlation coefficient, that's the R value. We'll round it. It's approximately 0.999. We don't just write the number without making a statement as to what that number is telling us. This is a strong positive linear correlation. Strong positive linear correlation. very close to 1, almost perfect. You could even say an almost perfect positive linear correlation. Right? I don't want you to be beholden to that table. Just use common sense. It's supposed to be really close to 1. That's as close as you can get without actually being a 1. So we're in good shape there. Determine the linear regression equation. All right. The model that the calculator is using is y equals ax plus b. We need the a and the b. Well, they gave us the a and the b. So we're going to rewrite this equation, keep the x and the y in your equation, but replace the a and the b with the numerical values. So y equals about 1.643 x plus 1.676. All right, so that's the line that best fits the data set. So if on paper I were to produce a scatter plot and draw a line to best fit that scatter plot, that line should have this equation if it's precise. Now, for ballparking, it might be somewhere in that neighborhood. It might not be exact, but it's going to be something relatively close to it. Right? So there's a few things that we did here that you might look at and say, well, I didn't see the point in that. Like, for example, the y1. When we put the y1 in there, you're like, well, what was the purpose of doing that? I just needed a regression between L1 and L2. This y1 business was useless. Actually, it's really useful because when I hit the y equals key after running this calculation, it took the most exact form of that regression equation and stored it in, store regression equation, it stored it into y1. So now when I look at my scatter plot, it's not only going to give me the points, but it'll give me the line as well. So when I hit zoom 9, I got the points and the line that goes through it. All right, a whole lot easier if I need to answer follow-up questions to do it this way. Definitely an adjustment, but if you practice at it, it's a useful one. Yeah, really. No, I'm not going to make you do the graph for this. Um, clearly, at some point, I intended to, but this is definitely enough. And again, it's my mindset changing from producing graphs by hand, getting a sense of inner workings, which I think you get enough of for, with some of the other graphs. Here, it's like, let's just get the job done. Like, I want a line that models the data. This will get me a line that models the data. So if I need to make predictions, I can get it off of this, right? So when we talk about things like, and I know it's a little disorienting because of the edits, so I apologize for that. But we talk about things like outliers and influential points. If you have a good graph, you can pick up on that information pretty quickly. Like I said, the next packet or two, well, every packet after this will be pre-edited. Yeah, so the definitions of outlier and influential points, you have it on your page 13. It was right after correlation and scatter plot, but I put it here in my edits, so we can still look at the same thing. So we'll talk about that briefly, and then we'll see how that relates to the graph. An outlier, we talked about that for a raw set of data, a single data set, but not when it compares two different data sets. outlier is a point that diverges greatly from the overall pattern of the data. So if you have a nice graph, it's pretty easy to see any outliers that might exist. Okay? You're looking for a point that's not consistent with the other points. So I look at that display on my calculator. I don't see any points that are greatly deviating from that line. So I would say that there are no outliers. There are no points that are far away from the line. Now, how you define far is really what ends up being the only confusing part about that. It's like, well, how far is far enough? Anything that's inconsistent with the data points, you can say, I suspect it's an outlier. All right? And as long as you can justify it, I'll take it. Right? If you have a point, I'll throw one in there, for example. Let's say you have a point right here. You might say, I think that's an outlier because all the other points are at least very close to the line. Some of them are actually on the line. This is the only one that's definitely not on the line. So I think it's an outlier. All right? As long as you can make a case. So a brief explanation is all I need. As long as you can make a case for something being an outlier, then that's going to be good enough for me. There is no mathematical approach to determine outliers other than visual. I mean, there are, but it's not. It's more mathematical statistics, like calculus based. So that's my patented answer. Everything's calculus. We also have something called an influential point. An influential point is a point that's an outlier, but only in the x direction. All right. So, different story. If you have an outlier, this would just be an outlier. If I had a point over here, so in the x direction, that would be an outlier in the x direction, making it an influential point. Influential font? I don't even know what I was trying to write there. All right, so if it's a vertical outlier, it's just an outlier. If it's a horizontal outlier, it's an influential. And again, these are not points that were in the original data set. I'm just doing it. But that really justifies it. So it's something big for both x and for y? Yeah, so if you have something, so you're only going to have an outlier in one direction or the other. So it's either going to be an outlier in x or in y. Because if it's an outlier in x and then also an outlier in y, it's going to fall on the line extended. In which case it's not really an outlier.
Well, I'm saying like, well, say you had 100 in x and have 22.
Oh, I see. That would be influential. Yeah, because the x is going to outpace the y by a lot. You just look at it, yep. But the graph ends up being your best tool to help you make the visual determination. All right, so you also have the ability, once you have the regression equation, to make predictions. So I'm just going to do it all right here because I know the notes aren't as nice as they could be for this. So if I wanted to make predictions, you can go one of two ways. You can, if you're given x, find y. If you're given y, you could find x. But that's all based on your regression equation. So you have an equation that relates x and y. As long as you have that, you have what you need in order to make predictions. So if I say predict the y value if x is 30 based on your model. Plug in the 30 here, simplify, solve, get your y value. If I say determine the x value that corresponds to a y value of 700, put in the 700 for y, subtract and divide, and now you have the corresponding value of x based on the model, right? So very easy to make predictions, just you're solving for one variable given the other, right? There are ways to do it on the calculator, though. This is not, for linear cases, it's not, I would say, 100% necessary. But for nonlinear cases, it's a little bit more necessary just because the numbers get a little out of hand. So I'll just show you, bless you. I'll show you the case where you find y when you're given an x. All right, so on the calculator, given x, find y. It's actually pretty not bad. So you have your equation. So this is assuming that you've done all the background work. You came up, I'll run through the calculations again. Stat calc 4. You did all this stuff. The key is that you have to store your regression equation. That's the one part that absolutely has to happen. Again, that's alpha trace. Like, recite that to yourself on the way home today so that you don't forget it. That's how important that is. All right. So again, that must happen. Let me even snip it in here again. Got it on the previous page. I'm putting it in. So again, alpha trace. If you're a TI-83 person, you have the fun process of hitting vars over to y vars, function, and then y1. Not as convenient. Not to say the alpha trace is convenient in and of itself. So again, alpha trace y1, alpha trace y1, alpha trace y1. Commit it to memory. Calculate. Gives you all the stuff that you need, right? But the added bonus is that it popped it in as y1 here. So that when you look at the graph, zoom 9, you have everything that you need. All right? So all that stuff happens first. Now, how do we get y given a particular x? So let's say predict y when x is equal to 70. This is how you do it. In your home screen. So quit out of your graph, go into your home screen. You're going to hit alpha trace. You're going to select y1. So alpha trace, you're going to select y1. And this is in your home screen. So in your home screen, you now have y1 and a blinking cursor right after it. Open a set of parentheses. Type in the number you wanted to evaluate. I want to evaluate it when it's 70. So type in the 70. Hit enter. 116.707. That would be your answer. This is function notation from algebra. Right? F of x. If I needed like f of 2, that's telling me to plug a 2 in everywhere I see an x. All right? Algebra skills are a little hit or miss sometimes in this course because sometimes people are taking this course to not have to take algebra-based courses. Like, well, I didn't want to take pre-calc. They told me to take stat, so I'm going to do that. That's one category of individual. If that's the case, then maybe you're not as comfortable with things like that. But what this allows us to do is to take our equation y1 and evaluate it for any x value that we want to plug in. So I want 70 to be plugged into my y1 equation for the x. Another way to do it would be to go into the table and scroll, but I don't want to scroll down to 70. And also, what if it's a decimal that I need to evaluate? What if it was find y when x is 17.482? That's not going to show up in the table. I don't want to do it that way. So, again, alpha trace y1, that's where my equation was stored. Put in whatever number you want. Put in a pi. Second caret symbol. I know there's a lag, but this is a little out of hand. This is supposed to be a computer-based emulator. Like, it's not supposed to have the same issues that you guys would have on your own handheld. There it is. So you can pop in anything you want. All right. Going the other way, getting x when you have a given y is a little more complicated. Probably a different story for a different day, so we're not going to worry about it. I mean, it's definitely a different story for a different day. Page 15.